In this lecture, we want to explore the origin of the softmax formula. Why does the softmax formula look like this? And if you think about it, softmax is used very often for classification, categorical data. And without softmax, what happened? Without softmax, many things may not work. Maybe we use other formulas, but softmax is the main formula that's being used, right? And it looks like this, where Z is the logics and P is what they call the probability of the class. Do you use softmax? Yes, everyone uses softmax, right? Yeah. Yeah, so as I said, the softmax is used very often. So it's really a foundation, okay? But have you ever wondered how softmax comes about? Maybe you want to ask yourself, yes, no, you have never think about this. How come? Why you never think about this? Or you have been thinking about this and you already have the answer. It's good. Or you have been thinking about this, but you couldn't find answer online. Yeah. And this kind of question is extremely important if you want to do deep learning, to understand the mechanisms, right? Why people do things the way they do. Okay, let's step back a little bit. Look at this example. Example of 4 classes, class 1, 2, 3, 4. And we pass data into a neural network. And the neural network crunch data, forward propagation, give 4 scores. 2, -1, 3, 0. This is what we are called logic score. Okay. The idea is using these scores, you want to choose one class, which is the class that this neural network is predicting. Choose one class, okay? How do you choose one class? There are many ways, of course, there are indeed in uncountably infinite ways, uncountably infinite as well. You can choose the maximum of the logics, you can choose the minimum of the logics, you can choose medium, you can flip a coin, uniform random with uniform random probability, randomly choose a class, or you can choose with some probability, right? Yeah. Okay, take maximum. You want to choose a class, okay, why not take maximum of the logics? Easy solution, right? Don't need softmax, just whichever logics is maximum, take that class, okay? Or we can equivalently choose take minimum, whichever logic is smallest, pick the class. There's no right or wrong about this, right? Either you pick maximum or pick minimum. There's no right or wrong about this, right? Anyway, the neural network will learn the logics that you want. Or you can take medium, right? But there's a problem with all this method. What's the problem? Okay. The problem is you do take maximum, take minimum. There's no gradient. There's no gradient to guide the neural network on how to output the logics. Okay, there's no gradient. Okay, let's suppose class 4 is the true label, true class. If you take maximum, you will choose class 3, then classification will be wrong, and then you get feedback. Okay, classification is wrong, and you tell the neural network classification is wrong, should be class 4, not class 3. And neural network, what can you do? Back propagate. There's no gradient. How to back propagate? You know you want to make a big logics for class 4, but now the big logic is class 3. How to back propagate, right? Okay. So if the neural network changes its weight a bit, come up with new set of logics, they say, now you get this. Is it still tell the neural network, okay, wrong. Answer is class 4. Your answer is wrong. So is there a way to guide the neural network to decrease the logics of class 3 and increase the logic of class 4? Okay, try again, still wrong. Try again, still wrong, right? Okay. So neural network backpropagation for neural network. The neural network needs a direction to move. And when there's no gradient, you want to do gradient descent, you cannot do gradient descent. Okay. Because maximum, minimum, medium doesn't work. Uniform random, oh yes, you can just always choose a class uniformly with a uniform random distribution. That's fine, but your neural network is not working very well. Okay, fine. You don't need gradient, right? So, well, obviously this doesn't work. Okay, we want to get the logics, and from the logics output some probability distribution that is a differentiable function with respect to logics, so that you can do gradient descent backpropagation. Okay, so if you think about probability distribution, there can be many. I can cook up many probability distribution, right? Let's suppose the logic is more than 0. Let's say the last layer is ReLU, so logic must be more than 0. Then I could make a probability distribution like this. Pi equals Zi divided by sum of Gj. Okay, fine. Or I can make another distribution like this. Pi equals Zi cube divided sum of Gj cube. Is also a valid, some kind of equation that does not violate non-negativity and normalization, right? For probability distribution. Okay. But really it's not really it's just arbitrary, right? Not a principled way, right? Okay. I can do either. It's nothing like I can train neural network, right? A more principled approach is from information theory, which computer science, computational people like to use information theory, right? You assume a probability Pi and some mean values M. Mean over the logics, right? Okay, mean value M. And with a probability distribution, sum of Pi must be equals 1. And Pi must be more than 0. Okay, this is another constraint equation which I not put here, which turned out to be unnecessary when we do the optimization. Okay, and we use Shannon entropy. Okay, Shannon entropy is widely used in information theory and computational science, right? And of course, in physics, this also is also a valid equation, a valid entity entropy, right? So what you want to do is the maximization of entropy. Okay, we want to maximize entropy. You want to maximize entropy with the constraint, with this constraint, the mean value constraint, Pi sum over Pi equals to M, sum of Pi equals to 1. Of course, each Pi must be more than 0. There's another constraint which I have not written here. And then S is the quantity we want to optimize. To perform optimization with constraint, we use Lagrange multipliers. In this case, I write the Lagrangian as S plus lambda 1 of the first constraint equation plus lambda 2 of the second constraint equation. And I differentiate the Lagrangian L respect to Pj. You have to go through the algebra, which I have not go through in detail here. You end up with this equation. And to find maximum, what do? You differentiate, you say whatever you differentiate to 0, right? Set to 0. And then we end up with this equation, log Pj equals to 0. And expect immediately you get Pj equals to exponential of minus lambda 1 Gj divided by normalization term, big lambda, capital lambda. You can see exponential of the softmax come from the logarithm of Shannon entropy. Come directly from there. Okay, this is one observation we make, important observation. Okay, using a constraint sum of pi equals to 1, we get pj equals to this. Okay, you can check back. You sum over pj, you get 1, right? And the arbitrary mean value m can use a fixed lambda, or we can choose lambda because m is arbitrary, lambda always arbitrary. Right? We can choose lambda to fix m, but m doesn't, in the end, is not important what the value of m is. Okay, so in the deep learning community, the convention is choose lambda y equals to -1. Okay, so now I want to compare to Boltzmann distribution in statistical physics, which is given by this equation. Okay, and here you can see -1 over t equals to lambda 1, right? T is the temperature of a system, right? Okay. Now I choose lambda 1 equals to -1 over t. And then we can explore the pi or pj properties of pj with respect to t. When t equals 1, with this logic, 2 minus 1, 3, 0, we get 0 0.25, 0 0.1, 0 0.7, 0 0.30. The logic with highest value 3 will have the highest probability. Okay, 0 0.7 here is highest. If I decrease t, you can see that the probability becomes sharper, as in logic with the highest value. The probability of the logic corresponds to the logic with the highest value tends to 1. When t equals to 10, all the probability become roughly the equal. Okay, when t equals 100, they are almost equal. T equals 0.1, we just choose the class with probability 1. In this case, class 3 with the highest logics. Okay, this is the property of pi respect to t. Okay, some other properties, right? Pi remains unchanged invariant when you replace, you offset the logic by constant. Gi replaced by gi plus constant. Okay, pi changes as t changes, right? Become more sharp as t goes to 0. You replace Gi by Gi times C is the same as replace T by T over C. Okay, I think that's it for this. Thank you. Thank you for watching this video. Okay, thanks.